Hello everyone, welcome back. What happens when a circuit has more than one independent source? Instead of solving the effect of all the sources together, we can consider one independent source at a time and then combine their effects. This is the basic idea behind the superposition theorem. In this video, we will understand the theorem from the basics, learn how to deactivate voltage and current sources, apply it to a simple circuit, and verify the result. Superposition theorem states that the response, that is the voltage or current in any branch of a linear circuit containing multiple independent sources is equal to the algebraic sum of the responses caused by each independent source acting alone, with all the other independent sources replaced by their internal impedances. This may sound complicated at first, so let's break it down. There are three main ideas: linear circuit, one independent source at a time, algebraic sum of the responses. First of all, what is a linear circuit? The theorem applies to a linear circuit. A simple example is a resistor, and we already know the equation V equal to IR from Ohm's law. For a fixed resistance, if the voltage doubles, the current also doubles. This linear relationship allows us to separate the effects of different sources and add them. So remember, superposition theorem is applicable to linear circuits. What does each source acting alone mean? Consider the circuit with two independent voltage sources. Suppose we want to find the current through the middle resistor. Normally, both sources are active. Using superposition, we solve the circuit in separate cases. Case 1. Keep V1 active, deactivate V2. Find its contribution, which is I1. Case 2. Keep V2 active, deactivate V1. Find its contribution, I2. Then I, that is the total current, equal to I1 plus I2. But what exactly does deactivate mean? How do we deactivate a source? The theorem says that the other independent sources are replaced by their internal impedances. For ideal sources, this gives us two simple rules. In case of ideal voltage source, an ideal voltage source has zero internal impedance. Therefore, voltage source is replaced by a short circuit when deactivated. Ideal current source. An ideal current source has infinite internal impedance. Therefore, a current source is replaced by open circuit when deactivated. Now, let us apply superposition to this particular circuit. We have V1 as 10 volt and V2 as 15 volt. R1, R2, R3 are equal, which is nothing but 5 ohms. We want the current through R3, taking downward as the reference direction. Consider case 1 where V1 is acting alone. First keep V1 equal to 10 volt active and deactivate V2. Since V2 is an ideal voltage source, replace it with a short circuit. Now our goal is to find the current through resistor R3. To find this current, we can first find the voltage across resistor R3 and then use Ohm's law. Since R2 and R3 are connected in parallel, they have the same voltage across them. That is why we first combine R2 and R3 into their equivalent resistance using the formula R2 into R3 divided by R2 plus R3. From that we obtain the equivalent resistance as 2.5 ohm. This equivalent resistance is in series with resistor R1. So now we can use the voltage divider rule to find the voltage across this parallel combination. So VR3 equal to V equivalent, which is nothing but 10 by 3 volts. Now that we know the voltage across resistor R3, The current through resistor R3 is VR3 by R3, which is 2 by 3 ampere or 0.667 amperes, and it flows in the downward direction. Now consider V2 acting alone. So keep V2 active and deactivate V1. Replace V1 with a short circuit. Again, we want to find the current through R3. So first we need to find the voltage across resistor R3. Since R1 and R3 are now connected in parallel, VR3 equal to VR1 equal to V equivalent. So to find their equivalent resistance, we need to consider R1 into R3 by R1 plus R3. So you get 2.5 ohms. This equivalent resistance is in series with resistor R2. So using the voltage divider rule, we get VR3 equal to V equivalent, which gives us 5 volts. Now to find the current through resistor R3, we just need to divide VR3 by R3, which is nothing but 1 amperes. And here also the current flows downwards. Adding the individual responses, we get the final result as 1.667 amperes, and the current here flows in the downward direction. But does this really give the same answer as the original circuit? Let's verify it. Now forget superposition for a moment and solve the original circuit directly with both sources active. Let the top node voltage be V. Applying KCL, V minus 10 by 5 plus V minus 15 by 5 plus V by 5 equal to 0. Multiplying by 5, we obtain V minus 10 plus V minus 15 plus V equal to 0, or V equal to 8.33 volt. The current through resistor R3 is given by I equal to V by R, which is nothing but 1.667 amperes. And because of the direction we have considered, this current is pointing downwards. Now compare the two results. They are exactly the same. Why do we say algebraic sum? The word algebraic is important here. If I1 equal to 2 ampere and the second source produces 0.5 ampere in the opposite direction, then I2 will be considered as minus 0.5 amperes. Therefore, total current I will be 1.5 amperes. So we don't simply add magnitudes, we add the responses with their signs. That's what algebraic sum means. What if there is a current source? Now consider a circuit containing a voltage source and a current source. That is V1 equal to 10 volt and we have I2 equal to 20 milliamperes. The same superposition principle applies here. Voltage source acting alone in the case 1. That is, we need to keep V1 active, deactivate the current source. Since an ideal current source becomes an open circuit, the right hand branch is open. Therefore, R1 and R3 are in series. So we get 10 divided by 5 plus 5, that is 1 ampere, and it is flowing in the downward direction. Now consider case 2 where current source is acting alone. Deactivate V1. Since an ideal voltage source becomes a short circuit, replace it with a short. Keep the 20 milliamperes current source active. Now the current source feeds the parallel combination of R1 and R3. Since R1 equal to R3 equal to 5 ohms, the current divides equally between the two branches. Using the current divider rule, the current through R3 is minus I2 into R1 divided by R1 plus R3. The negative sign is because we are taking the downward direction through R3 as positive, while the current contribution from the current source flows upwards through R3. So we obtain minus 10 milliamperes, and the negative sign here means that the actual current is 10 milliamperes upwards. So I equal to I1 plus I2, or 1 minus 0.01, which is nothing but 0.99 amperes, and here the current flows in the downward direction. What happens to dependent sources? Suppose the circuit also contains a dependent voltage or current source. Should we deactivate it? No. Only the independent sources are considered one at a time. dependent sources remain active. What can we find using superposition? Superposition is used to find a voltage or current in a linear circuit. What about power? Superposition is not directly applicable to power. If I equal to I1 plus I2, then P equal to I square R, which is nothing but I1 plus I2 whole square into R, which is not simply I1 square R plus I2 square R. Therefore, first find the total voltage or current using superposition and then calculate the power. Can superposition replace KCL or KVL? No. Superposition tells us how to separate a multi-source circuit. We can then use KCL, KVL, nodal analysis, mesh analysis or any other suitable method to solve individual circuit. What if there are more than two sources? The same idea applies. If there are n independent sources, consider one independent source active at a time. You will obtain n cases, then add all responses algebraically. That's all about this particular video. I'll see you in the next one.